Hello, welcome to the next video of the lab one. In this, we are going to start our first task of displaying the seconds counter on the onboard 7-segment display in the Basys 3 board. So we'll start with the ViewOrder 2022.1 in the ML edition. So we'll start with the create project. Next. So here we'll make sure that we create a folder where there is no space here. Make sure. And this will be a lab 1 part 1. So click on next. So here we are not going to specify any Verilog files, so I'm not going to specify here anything. Then here, in case here you need to make sure that you have the Basys 3 board added in your view order. So here you can see that I have the Basys 3 board already added in my view order. In case it is not added, the process is very simple. You go to this link on the Digilant one, and where they have mentioned the how to install the view order as well as how to add the boards. So basically, you need to download the corresponding board files from this website, then extract that board files. And in that board files, you will see that there is a new folder, and in that you have the board files. These board files you need to copy in your ViewOrder installation directory in this location. Once you do that, you need to close the ViewOrder and start the ViewOrder again, and you will see that the Basys 3 board which is present in your board list. Okay. So once you do this, click on next and then finish. So this will create a project in your folder which you have specified in the beginning. So this is my project link. Now in this project, I'll be creating the various design files to get the corresponding task. So I'll click on add sources. Here you can see that I have three options. One is to add the constraint, one is to add the design, and one is to add the simulation sources. So in the beginning, we will start with the design sources. Then we will add the simulation sources to do the test bench writing. And then we'll add the constraint when we are going to generate the bit stream. Okay. So let's start with the design sources where we will write the Verilog code for our desired functionality. So here our aim is to design a clock. So let's see lab 1, part 1, and then it's a digital clock. Okay, so this is my first part. Or we can give the simple name so that we can reuse the file later. Okay, so we'll use the digital clock. Okay, just keep the name simple. Now, for this digital clock, we need to decide what are the interface. For example, the first interface in our digital clock is my input clock, which I'll get it from the onboard oscillator, and it's a 100 megahertz clock for the Basys 3 board. Then I can take the reset input. I can take it from the, say, push button, onboard push button. Then my output will be the output to use. Okay, so one is to decide which 7-segment to use because there will be 4 7-segment display on the Basys 3, and one is to decide what to be displayed on the 7-segment. So in that case, if you look at the data sheet, you will see that there are 2 inputs to the 7-segment. One is the board 7-segment, one is called as the anode. This is used to decide which 7-segment to be selected at the particular time. And since there are 4 7-segment, it's a 3 down to 0. Then in addition, you have the board 7-segment display cathode, which decide what to be displayed on the 7-segment. And this is the 8-bit signal. So once you enter this data, the first draft of the Verilog file will be created in the URL. So you can see that this is the module is created with the name digital clock. So now we will quickly discuss the what are the things we need to design to get the desired functionality. Okay, so as discussed before, we have the just 1 minute. So we have the module. So let's see, this is the module. Then input is the 100 megahertz clock, and the another input is the reset. And the output is the 7-segment display. So we have the 4 display here. Okay. So this is how the 7-segment looks like. Okay. So these are the 4 displays we have here. And then we provide the 2 outputs. One is the 4-bit signal, one is the 8-bit signal, that is the cathode, and this is the anode. So what we need to do from this 100 megahertz signal, we need to generate the 1 hertz signal, because we need to have the seconds counter which increments at every 1 second. So we need to use some clock division circuit to get the 1 hertz signal. Then we need to design a counter. This counter will be run by the 1 hertz frequency, and it will give the increment the counter. This is the mod 60 counter because we are designing the seconds counter. And the value of this counter need to be displayed on the 7 signal. Now, since this counter output is in the binary, we need to convert this binary to the BCD so that it can be displayed on the 7-segment display. Okay. So basically, we need to design the clock division circuit, we need to design the counter, and we need to design the binary to BCD converter, and then we need to integrate on the 7-segment display. Now, another thing is, now to generate from 100 megahertz to 1 hertz, it's a significant clock division circuit. So we are going to use the inbuilt IP, which is the clocking wizards in the Vivado, which can reduce the 100 megahertz to some smaller frequency. And then we can use the Verilog RTL code to reduce the further frequency to the 1 hertz. So in the next, in this video, we are going to focus on the how to get the 1 hertz frequency from the 100 megahertz corresponding input frequency. Okay, so this is my input clock of 100 megahertz from the oscillator. This is present on the Basys 3 board. This is my active high reset. So this is the 4-bit select signal for on-board 7-segment display. Okay. And this is the 8-bit data signal for onboard 7-segment display. Okay. Now, what is my task 1? Task 1 is to do the clock division. And as I told you, you can either write a pure Verilog code to get the 1 megahertz frequency from the 100 megahertz, but we are going to do it in the 2 steps. We are going to use the inbuilt clock division IP, which is more efficient to perform the clock division, but it has a limitation on what is the lower frequency you can generate. And from that lower frequency, we'll generate the 1 hertz from the RTL Verilog code. So first task is to generate lower clock from 100 megahertz clock via clocking wizard IP. Now, this clocking wizard IP, which is present in the Vivado IP catalog, it uses the internal PLL and MMCM, that is the clock module inside the FPGA, and it performs the clock division. Okay, so we are going to use that. Now, the lowest frequency it can generate is the some around the 4.8 megahertz. So what we are going to do is that we are going to generate the frequency of 8.388 megahertz from this module. And then we are going to divide this 8.388 megahertz by 2 to the power, say, 23 to get the 1 hertz frequency. Okay. So generate 8.388 megahertz frequency. Again, you can come up with your own numbers also. That is fine. So what we are going to do is to go to the IP catalog. In the IP catalog, you can see that there is a clocking wizard. This clocking wizard is a very powerful tool. So in this case, you mention what is your input clock frequency, input clock. So in our case, input clock is clock 100 megahertz. So that is the 100 megahertz you can see here. Okay. Then you mention the what is your output clock. Your output clock is 8 megahertz. Okay. So 8.388 megahertz. Okay. So obviously you won't get the exact clock. So it is, you can see that here you are getting the 8.38798 because it depends upon the inbuilt divider and multiplier circuits present. So you are getting very close to it. And if you divide this 8.388 by 2 to the power 23, you will get the approximate 1 hertz clock. Okay. So here you can see that I have reset clock input and the clock output and the lock signal. Lock signal goes to 1 whenever there is the output frequency is exactly matching the desired frequency. But we don't need it, so we can remove that one. Okay, so these are the settings are there. We don't need to go into the much detail. So with this, we click OK. Okay. So now we need to integrate this IP, which we have just added in our view project. So what we are going to do is that for this IP source, we are going to go to the instantiation template, and we are going to copy the how to instantiate this IP in our project. So we are going to copy this in our main module. This is called as the IP instantiation. This is the name. So we'll say clock 8M. So this circuit produces the clock 8M. Since we have given the similar name as our requirement, so we don't need to change much here. So clock 8M, we can define this as a 1-bit wire signal. Then reset is same as the reset input, and the clock 100M is same as the input. Okay, so the output of this circuit is the clock 8M. Now, you can verify the functionality of this by writing the test bench, but we are going to do that in our next video, not in this video. Okay, next lab, not in this lab. So now we completed the first task of generating the 8.3 megahertz. Now in the second task, which is our task 2, what we need to do is that we need to generate 1 hertz clock from log 8M. Okay. And for that, we are going to write our own RTL Verilog code, because this unit, which is there inside the FPGA, cannot generate such a slow 1 hertz clock. Okay. So now what we are going to do is that basically by using the counter, we are going to design the circuit. For example, you can see that in the counter, so let me go to the whiteboard and explain the concept. Suppose I design a counter, say 2-bit counter. So what are the values of the counter? 1 minute. So the values of the counter is 0, 0, 0, 1, 1, 0, and 1, 1. And this counter goes like this. So you can see that if you select this bit, your input frequency is divided by 2. And if you see this unit, your input frequency is divided by 4. Okay, so this is how the counter works. How this works? So for example, suppose this is my input clock. So at every positive edge of the clock, you can see that this bit is changing. So you can see that if this bit is 0, this will be goes to 1. Then at this it goes to 0, 1. Uh, sorry. So at this point it goes to 1, at this point it goes to 0, at the next positive edge it goes to 1, at the next positive edge it goes to 0, at the next positive edge it goes to 1. And this bit, you can see that it 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 goes to 1 at the every second positive edge, and it goes to 0 at the every second positive edge. So you can see that you can generate the any clock of power of division by power of 2 using the counter. And suppose you have the input clock of say 8. So suppose you have your requirement is the 1 hertz clock, and if you multiply it by 2 to the power 23, you will get the approximately is 8.388. So basically, when you divide this 8.388 by 2 to the power 23, basically you choose the 23rd bit of the counter, you will get the 1 hertz clock. You can go to the digital circuit concept to understand this in more detail. Okay, so what we are going to do is that we are going to generate the clock of 1 hertz using the our own model. So we'll call this as a clock division RTL model. Okay, and this clock division RTL model, it is a generic model, so we should be able to divide it by any factor. So for that, we will uh, use the parameter which tells what should be the division factor. So it should be the count factor. Okay, so if you want to divide it by say 23, it can be 1 minus 1. That's how we are designing the code. But you can modify the code as per your convenience. This is the corresponding instance name. Okay. And then this will have the input, which is the reset. Then it will have the input, which is the clock in, which is my clock 8 megahertz. And it will have the clock out, which is clock 1 hertz. Okay, so this is the clock, the model instantiation. You can do it after writing the Verilog code, but it will be good to have the clarity on what code you are writing and what are the inputs and output. Now we'll write the corresponding Verilog code for this. So I'm adding the file with this name. Okay, so uh, this I can do it later. So you can see that the corresponding file has been created. So now we need to write the corresponding code for this one. So this is the RTL module. So the first one it accept is the parameter. The parameter is same as this one. Default value is 22. Input is reset. Input is clock in. Output is clock out. Okay. So again, as I mentioned, this is the simple counter circuit and we need to select which bit we want to design. So for the counter, it's a sequential circuit. We'll have the next and the register variable. Okay. So we'll have the register count reg. Okay. And it should be the size is at least this one down to 0. And since it's a sequential circuit output, we'll initialize it to some known value. And the range will have the corresponding combination of circuit output, which is the next value. Then we'll design a sequential circuit of the counter, always at cos edge of clock in. If reset, we will have, once reset is equal to 1, we will make the clock register is equal to 0. Again, we are going to use the blocking statement in the sequential block. Is equal to count next. Okay, so this is the sequential part of the counter design. Then combinational part where we increment the counter star count next is equal to count range plus 1. Okay, so this is where we have designed the counter, and now our output clock will be the particular bit of the counter. So clock out assign clock out is equal to count range is equal to the particular bit. So here, when you select the 22nd bit, that means we are going to get the division by 2 to the power 23rd. Okay. For example, we select the 0th bit, we are going to get the division by 2 to the power 1 because first bit gives the power division by 2. If we select the first bit, we are going to get the division by selected by 2 to the power 2, 4. Okay, so that's why when we select the this bit, we are going to get the division, clock division by factor 2 to the power count plus 1. Okay, so with this, we have completed the this circuit where we have designed the we have designed the clock division from 100 megahertz to 1 hertz using the clocking IP, which is there inside the Vivado, and using the RTL code. So we divided the clock first in the beginning from 100 megahertz to 8 megahertz, 8.388 megahertz to be exact, and from 8.388 megahertz to division by 2 to the power 23, we get the clock 1 hertz. In the next video, we will complete the rest of the model.